So we will stop the recording after the main presentation, so you can be as uninhibited as you like with your questions. So it's a real pleasure today to have Tim Brady joining us from California. Apologies, Tim, it's very early with you, I know that. We're very grateful for you to be up at this time on the West Coast to talk to us. So Tim is he's associate professor of psychology at UC San Diego. He received his PhD from MIT's Department of Brain and Cognitive Sciences, and then did a postdoc at the psychology department at Harvard, at the Harvard Vision Lab, and he's now the principal investigator of the Vision and Memory Lab. And as you'll see, Tim's been doing some really lovely work at this interface between perception and memory, and I think it's just perfect material for a Consciousness Club seminar. So we're really looking forward to your talk, Tim, and over to you.
Cool. Yeah, so I will talk, I don't know, mostly about this preprint we posted with Michael Cohen and Jonathan Keefe. If you study consciousness, you probably know of Michael. I recruited him to help me with this because I know nothing about that for the most part, and so just you'll see that as we go that I have some kind of expertise on this, but it's not really about the sort of consciousness questions. But okay, so as he was just saying, my lab sort of broadly bridges sort of perception and memory. We think of ourselves as at this intersection where perception meets memory is a really interesting place to be, because you can use sort of psychophysical methods and like the methods we have of perception and the understanding of perceptual representations to understand questions that are a little higher level. So we try to sort of measure precise visual representations, not only online during perception, but also examine the effects of attention on those visual representations and look at what they look like in working memory and long-term memory, and examine how items are distorted by other items that are present, and ask sort of questions about visual representation that go beyond basic perception questions. And today I'll just talk about one small slice of this, which is sort of take on continuous reproduction tasks, sort of the method of adjustment as a measure of visual representation. So if you ask someone to report exactly what was there and sort of describe it with a color wheel or something like that, what does that mean? And I'll tell you a little bit about working memory and long-term memory, and then talk a little bit about how we think this applies to perceptual awareness paradigms. So the sort of linking thought will be sort of methodsy. What do you get out of these tasks? And the theoretical take home will be something like, it doesn't seem like we see a lot of all or none failures of awareness or memory in these tasks, even though the most natural interpretation of them is that you do. And that sort of consistent with a pretty simple signal detection theory like continuous variation story, we see all sorts of high confidence errors and sort of perceptual false alarms that seem consistent with a pretty simple story about what's going on in these tasks, even though they seem like they give complex data. And I mostly wrote this talk for people who maybe aren't super experts at this sort of method and stuff. So if there are some people here, I saw some of the Bayes Lab folks here, then you'll have to just bear with not being the target audience. I'm sorry for that. Okay, so let's start by doing just a what do I mean by this kind of task? And so I'll have you guys do a pretty simple visual working memory experiment to start. So I'm going to show you some squares, and then they're going to fill in with shapes. And I want you to do your best to remember exactly what shape is in each location. And the shapes will continuously vary. So it's a hard task to remember the exact shape in each location. Okay, so these are the locations. Try to remember the exact shape that's in each location. Some delay happens. And now we ask you, hey, in this bottom location, exactly what shape was it on this shape wheel? And that's a hard task with 6 shapes. It's almost impossible task, right? And you might click something like that. That's actually the right answer. That was the shape that was in that location. But but you might click in the wrong spot, right? Can you see my cursor? I forget how this works. I haven't done this in a while. You can see my cursor, right? Okay, so you might click there, and then we'd call that a negative 20-degree error because you're sort of 20 degrees away on the wheel. And you might click there, and then we'd call that a positive 20-degree error because you're 20 degrees away in the other direction. And of course, you might click way over here and be 180 degrees off. And this kind of task is a really nice measure of visual representations and has become really popular. It's basically just the psychophysics method of adjustment, but as applied to this kind of wheel of spaces. And as many of you may know, the sort of thing that happens when you do this task is that you get an error distribution across hundreds of trials. And here's what that tends to look like. So if I ask you what shape was in a location, you'll often be near zero. That means correct. That means you were close to the right answer. But you'll also often choose things totally on the other side of the wheel. Like I was showing, you might choose things 150 degrees away. And for many years now, for a decade now, the standard view of this task has been this sort of mixture modeling approach that you may have seen. Effectively, people, including Zhang and Luck, looked at this distribution and said, it looks like really there's two things happening here, right? It looks like there's something like what happens when you have no idea at all and you guess randomly. And if you guessed randomly, you'd be equally likely to get a 180-degree error or a 0-degree error or a 50-degree error. And so you'd have a flat distribution, a uniform. And it also looks like sometimes you do remember what you saw. And on those trials, you get near zero, but with some noise. There's some precision variation in how accurately you can do that. And so this kind of approach to understanding these distributions has been, I don't know, used in somewhere in the order of a few thousand papers in different literatures trying to understand what is going on. And what they said, and Zhang and Luck said, is in working memory tasks, if I give you just one item to remember, you tend to be very accurate. You tend to be near zero. That is, you don't have any really far away responses because you've only got one item in mind. If I give you 3 items to remember, then you tend to be very accurate, but every once in a while, you'll make a really large error. And what happens when you go from 3 to 6 items is, as you can see, the center part of these distributions look almost the same. All that seems to happen is that there's just mostly more guesses. And so they said, look, what's happening when you give people 6 items in memory is 3 of them just turn into guesses. 3 of them don't make it at all. And 3 look just like 3 items in memory, right? So they were saying this looks like just basically the same thing that happens with 3 items on the display plus more guesses. And this is not just for working memory. All sorts of more awarenessy paradigms like the attentional blink have had the same approach taken to them. So if you don't know, the attentional blink is this idea that if you show someone a very rapid sequence of items, in this case, you have to remember the orientation of the red and green gradings amongst a bunch of noise. Then if we look at your error in reporting the second target, if the second target happens a long time after the first target with 9 items in between, you tend to be pretty accurate. Mostly responses near the right orientation. But if it happens quickly after the red one, only 2 items later, when your attention is conceivably still processing this first target, then you tend to have much worse errors. And in fact, you once again find that it looks largely like a change in guess rate, as though items were discretely lost. You just don't see them sometimes in the attentional blink, is the claim of these papers. Okay, so those are just 2 examples of this kind of method and this kind of approach. This idea that we can use this kind of method to measure 2 things, the precision of memories or representations, broadly speaking, and the number of items that actually made it into representation is really broadly appealing and has been used in things like attention, like those attentional blink studies, and things like iconic memory, and things like working memory, and things like long-term memory, with, as I said, more than 1,000 papers using this kind of method to try to figure out which part is the cause of various things. For example, the correlation with intelligence, the claim comes from guess rate, not from precision, for example. Okay, so these are the kind of approach, and broadly the claim that I'm going to be interested today is that there's some idea here that items are often lost from perceptual awareness or memory in this all or none, really discrete manner. They don't just get noisier, they just go away. They're just completely lost. And that seems like a really deep claim about the nature of perceptual awareness and memory, right? Okay, so we have lately been suggesting an alternative way of thinking about that data that says those long tails are just sort of the natural consequence of how it had to be. Those sort of far away errors just had to be there. And we shouldn't think there's 2 things going on here, guesses and precision. And the model that we proposed is basically just signal detection theory, if you're familiar with that, which is like the most minor generalization to continuous spaces. And I'll explain what this means, but broadly, we've been proposing a model that just combines signal detection with sort of some measure of how confusable items are on that wheel, on that shape wheel or color wheel. Okay, signal detection theory, for those who don't know, if you want to think about signal detection theory in a really simple memory experiment, imagine I showed you this purple color, you form some complicated memory trace of it, and then later I ask you which one of two things did you see? Did you see this green color or did you see this purple color? Really simple experiment, a really simple task. And the way signal detection theory conceives of this is that you're computing some sort of memory match signal, some sense of how familiar this green thing is given what you encoded, and some sense of how familiar this purple thing is given what you encoded. And we can think of that like this over here. You've probably seen these two distributions before. So that greater familiarity is to the right. So stronger memory match is to the right. I use familiarity colloquially here, not like in a technical sense, just like it feels more familiar because it matches memory better. And the standard signal detection idea is basically, well, the purple thing you saw is likely to match memory better than the green thing you didn't see. So there's a shifted rightward. But also there's really noise in this process. So even things you didn't see sometimes feel familiar to you. They sometimes match memory. And this is like a matching a multi-complicated memory signal. So there's of course going to be lots of variation in how well any given stimulus matches, even for a color. And so what this amounts to is that effectively what this says is just there's noise in the average familiarity value of each one. So on a given trial, purple might feel really familiar and green might feel not familiar, and you'd be very confident you saw purple. Whereas on a different trial, you might get a bad sample, you might get bad noise, and green might feel slightly more familiar than purple. And so if we conceive of this as the underlying decision process, we can go from how accurate you are back to like how far apart these distributions were, D prime, like how accurate your internal separation was. And this is like the null hypothesis of decision making, right? This is like the simplest possible model. And the insight of this model, I'll tell you about this TCC model that I'll tell you about in this 2020 paper, really is simply explained just by switching to 4 AFC instead of 2 AFC. That's like the simplest way to think about it. Imagine I showed you purple and then I asked you which of these 4 colors did you see? Well, effectively the way we think about this signal detection problem is that the thing you did see, like the thing 0 distance from what you encoded, gets a big boost in familiarity. And the thing you didn't see gets none. It's far enough away that we can think of it as basically having no familiarity at all. And so for this light green, and even for this dark green, that's probably reasonable, right? This dark green doesn't really get any boost in familiarity when you see purple. And so we can think of the dark green as just another distribution centered at 0. And so usually signal detection theory, if you think of like a 4 AFC signal detection model, just says all the distractors are centered at 0 and the target is centered at D prime. But in a continuous space, that makes no sense, right? Imagine I showed you a purple 1 degree away on the color wheel from this purple. You wouldn't even be able to visually tell it apart from this purple. And so of course you'd choose it equally often to this purple. It's an impossible task, right? So 1 degree away on this color wheel, you'd get the same boost in familiarity you got for the actual color you saw, just for perceptual limits, right? And so it sort of must be the case that similar colors like this purple are going to have some shared boost. They're going to have some boost in familiarity from having seen this purple. And so effectively what that means is like this dark purple is like pretty similar. Oh, did the screen actually freeze? Or just for you? Okay. This dark purple is going to have some boost in familiarity just from having seen this light purple. And you can think of this as a boost in familiarity. You can also think of it, again, there's this complex memory signal, and this dark purple is going to match it on average pretty well, even though it's not going to match it perfectly. And so it's going to have some boost in match signal relative to a really far away target. And that's it. That's basically the whole insight, that has to be true and that we can just measure that. And so if you think what the implication of this would be, well, what it means is this dark purple distribution of familiarity signals is going to be shifted upward, right? It's not going to be quite as high as light purple, but it's going to be boosted relative to dark purple. And so you're going to be much more likely to have dark purple be the most familiar than green, right? Because on average, there's going to be a big boost for dark purple. It's going to match memory signals better. And so this is how we conceive of this. just this gentle generalization of signal detection theory to say the foils, the other items, are not always centered at 0. They're centered at some match signal that depends on how similar they are to the target. And now if you want to give someone, say, a color wheel, you say, hey, what color was it on this whole color wheel? You can just think of that as a 360-degree forced choice task. There's 360 items you have to choose between. The ones that are very, very similar to the color you saw are going to have big boosts. They're going to match memory pretty well. The ones that are far away are not. And then effectively, you just have to ask, what is this shape? Like, what is the shape of this spreading function? Like, how much does familiarity get boosted depending on how far you are on the color wheel or shape wheel or whatever wheel you're on? And there's tons of reasons to suspect this would be basically an exponential-ish function. Like the perceptual discriminability is going to be exponential, like Fechner. The universal law of generalization, sort of how much we tend to generalize across stimulus spaces by Shepard, would suggest that. Nostovsky's done lots of great work on this in recognition memory and similarity spaces. There's tons of reasons to think that would look something like that. And I'll talk about that a little more later. What we do in this set of work is we just try to basically ask people how confusable they are by just giving them a similarity task. We just say, hey, how similar are these two things on a Likert scale? That works pretty well, or we have more complicated tasks. But effectively, we think this is basically a property of the stimulus space. This is something like what the tuning functions look like for color or something, right? It's like how far apart colors tend to be. And we leave this completely fixed across participants and tasks, and like this is a measure of the stimulus space, not something that varies. It's not like a precision of memory. It's just a fixed property of how confusable things are in the stimulus space. And so, okay, so what does the model you end up look like? Well, it looks a little complicated, even though it's this gentle generalization of signal detection theory. It looks complicated because now it's a 360 alternative force choice. And if you write that down, well, now you have 360 distributions, right? Because each color is competing to be the max signal. And so what you end up with is colors that are far away have 0 familiarity spreading to them, and so they're all centered at 0. Colors that are similar to the purple you saw get some boost depending on how similar they are. And so on a given trial, you might think, purple is the strongest signal, but you also might sometimes think, green is the strongest signal, just depending on the noise. I find people like seeing the signal detection distributions for 2 things, but with 360, this is not very helpful. So I like to explain it instead like this, which is just like one trial and thinking of the signal detection part as noise instead of sampling from a normal distribution, even though those are the same thing. So before you see something, all the colors feel equally unfamiliar. They're all centered at 0. There's no familiarity matched to any of them. When you see this green, it boosts familiarity for this green color, but also for similar nearby colors. That's this fixed perceptual similarity function, and doesn't boost any familiarity out here. Now during delay, this signal gets corrupted by noise. So we just add noise to this. Different amounts of noise will result in different results. And then at the end, what we have is like the likelihood each color is the target, effectively, is what this familiarity value is. And we just choose the maximum. If our task is just, hey, what color was it? So we might report this color here on this trial. Okay, so that's like the idea. It is this like gentle generalization of signal detection theory. But what happens when you have this is that this diminishing returns, this exponential function, basically makes the data look like what we find in all those tasks. So if you have no signal at all and you have a bunch of noise, then which item is the strongest at the end of the trial is going to be totally random with respect to what you saw, and you're going to get uniform guessing here. If your D prime is really high, like if you have a really high signal relative to a very small amount of noise, you're not going to ever have the strongest signal come from out on this tail because there's just not enough noise, right? So you're only ever going to have ones that already got a big boost in the signal be the winner. And so you're going to get this very tight distribution. But in these in-between zones where you say your signal and your noise are about equal in volume, then of course it's going to be possible that on some trials, these colors out here get lucky noise and they win. And on other trials, but you're going to be a little bit more likely to have the ones in the center win because they got a boost in the signal, not just in the noise, right? And so effectively the story here is just like there's this fixed function of like confusability in shape space or color space or orientation space or whatever. And then you just add noise to it. And that the natural consequence of that is distributions that look like this. And so the prediction here is basically all memory errors, and then I'll talk about awareness errors, basically all look like one of these distributions. Now, there's not like multiple ways these distributions change, that for a given stimulus space, it's just one knob. It's just the signal to noise. It's just the D prime. You can make it worse or better, but you're never going to find separable guesses and precision. They're just one thing that changed together. And I won't show you all the evidence for this, but we found lots and lots of evidence for this, something like 40 experiments now, trying to find exceptions to this without finding them. And so here's, for example, set size. So if you just have one item in working memory on a color wheel, people have a very high D prime and it's very tight distribution. By the time you get down to 8 items, it's a much lower signal to noise ratio for each item. They're all noisier, and that results in this long tail, but there's no evidence for anything else. It feels like this lands exactly where you'd expect it to land with that same fixed function. And that's true for, here's shape. So here's that shape task I gave you. Here's 1 shape, 3 shapes, and 6 shapes. And again, it looks like just turning the noise up as more items are presented. And we've done this across, I don't know, I think 6 or 7 stimulus spaces where we measure different confusability functions and predict different error distributions, and it always seems to work pretty well for matching the error distributions. And this is not just true in working memory. This exact same thing happens in long-term memory. So I show you 100 objects and colors, and then I ask you what color was this one. An hour later, you get the exact same distributions and the exact same model fits, like literally the exact same model, no changes. So we think that across most of these domains, it makes a lot of sense to say, well, there really wasn't 2 things we were measuring. There was really only one thing we were measuring, just this sort of signal to noise ratio, and not really 2 different things. And of course, I just showed you that in some way because I just showed you, look, this model that has just one knob fits all that data. But you can also really directly ask this question. You can say, what if, what would it mean if people are measuring 2 things in all those papers and they're finding dissociations? They're finding sometimes only one changes and not the other. How could it be there's only one thing? How could it be there's just signal to noise, just D prime? Well, we can just take all those data sets and look at only ones that use the exact same stimulus space. Because remember, different stimuli spaces will have different confusability functions. They'll have different similarity structure. But if we use the exact same stimulus space and look at all of the tasks and fit mixture models to them, what we should predict is that really there are not 2 separate parameters. They never dissociate if you keep your stimuli constant. And that's broadly what we find. So here's a graph where it's a little complicated. And if you don't get it, that's okay. This is the mixture model parameters fit to 25 or 30 experiments we ran with different conditions in working memory and long-term memory, all using the exact same color wheel. And this is the guess rates they estimate, and this is the precision values they estimate. And what you can notice is that they are all along one line. That is, when guess rate goes up, precision goes down, imprecision goes up. It does not look like what you'd expect if there were 2 separate knobs here, right? If there were 2 separate things, you should sometimes find a really high guess rate with really strong precision, or a really strong, or really remembering many of the items, but with lots of noise, like down here. But you just don't find anything there. Instead, you just only find they land on the same line all the time. And you can create situations here where it looks like only one changes. Like when memory is very bad, you're going to find that there's a lot more vertical change than horizontal change. A change from 21 to 22 degrees in standard deviation is imperceptible, but the guess rate changes a huge amount in that area. So this is sort of nonlinear in a way that can explain why people sometimes find dissociations, but it doesn't seem like there are really 2 things. It really seems like there's just one parameter. And these all land on the line that our model says they have to land on. This is the relationship between them. Okay, that last part's a little complicated. But the idea is there's really only one way representations are changing here, just getting better or worse along that line, not separate guess rate and precision. Okay, so this model we've argued, it's basically just says, well, what if you just take signal detection theory, but you say, well, look, not all of the alternatives are going to be centered at 0 familiarity. The ones that are really close in a continuous space can't be. So what if we just use this exponential instead? And I think so the thing to keep in mind here is that most of the magic happens because this function of how confusable items are with a target is non-linear. It's not like just that the further away you get on the shape wheel, the more likely you are to confuse it. That wouldn't create the right distributions at all. The long tail of errors happens because all of the items far away from the target are all sort of equally not similar to it. And if you want to think about why that is, I think people often feel like it's kind of weird, but actually it's like the only way it could have been. So I already mentioned, Shepard and Fechner and all these reasons to think that, but even really simple models of representation in vision suggest it had to be this way. So imagine you see this item and you think of this as like a 0.5, like you're storing it with one number. That's like, I think, how people intuitively approach this task. Like, this is orientation 0.5. And then there's noise. And so sometimes I encode it as orientation 0.65. And if that's your mental model, then when you see error distributions that look like this, what you expect to happen as memory gets worse is that it just gets wider, right? It just gets wider as you add more noise. And I think that people have that intuitive model, even though nobody thinks we're storing orientation as a single number in angle in our mind, right? Instead, oh yeah, and so in this framing, this long tail is surprising. Like, why does it look like this? And then people propose this guessing process, right? But instead, we actually think orientation storage looks something like this, right? What we have is like tuning functions for orientations. And we have a really high dimensional representation of an orientation. When we store this orientation here, we store it as like, well, it activates this tuning function, but it doesn't activate any of these, and it activates this one a little and this one a little. There's a high dimensional rich representation, right? It's not just one number. And if that's true, then when we consider how you'd store this orientation and how you'd store this orientation, we wouldn't say those are 0.4 away from each other on this axis. We'd say, actually, these have zero overlap at all. They don't even activate any of the same tuning functions. They activate none of the same cells at all. And so what this does is, if you just think it looks like this, that there's like tuning functions, for example, then it's going to produce a sharp fall off with distance. That is, the overlap between two orientations is going to fall off very quickly as you separate farther apart, right? And so this just says, well, if you thought it looked like this, any high dimensional representation for the most part of a stimulus, but especially a tuning function one, then it had to be the case that as you get farther apart on this wheel of orientations or shapes or whatever, you just end up in a place where there's no overlap at all between them. And so you end up with this nonlinear representation. And this idea that this sort of nonlinear distance function is pretty naturally explained by like tuning functions. It's pretty similar to like the neural resource Paul Bayes model of working memory stuff that connects strongly to this model through this insight, basically, and to representational similarity stories that effectively say that when you have high dimensional representations of stimuli, you're going to end up with really far distances between anything that's not close. Just in 20 dimensions, everything's going to be far apart if it's not really close, basically. Okay, I don't know. So we haven't done much with tuning functions. The Bayes lab has done lots with this if you're interested in it. But we have just asked what happens if you just take our stimuli and just throw them into a deep net. So this is just a convolutional neural network here. And as a reasonable, what does a high dimensional representation of the stimuli really look like in the visual system? Can't do much better than just throwing it into a convnet. And what you get out of this is 1,000 features for this stimulus and 1,000 features for this stimulus. And you can just ask, how far apart do they tend to be as a function of how far they are in orientation or shape or color space? Without any assumptions about tuning functions, just let the deep net do it for us. And what you find is that you find this exact same nonlinear overlap. You find this exact same thing where human similarity and the CNN overlap fall off in the same, almost exactly the same way for most stimuli that we've tried for color, orientation, and faces. Okay, so the idea is that just boring signal detection theory with this nonlinear, how confusable items are with each other, explains all of these continuous reproduction tasks, and that it had to be that there was this nonlinear fall off. It's basically what you expect from just a CNN model. It's what you expect from tuning functions. It's just sort of the only way it could have been. contrary to the intuition that it should just get noisier in one-dimensional space, which doesn't really make sense. Okay, so this is the model that I hoped to convince you of, that I could now use, having convinced you to ask questions about awareness. Okay, so I said this is sort of method-y, and I mean that in the sense that the mixture model, that exact same technique of fitting a guess and precision mixture, has been widely applied throughout questions about perceptual awareness. For example, backward masking, the attentional blink, iconic memory. I'll talk about all of these in turn. And in these situations where you flash a stimulus up really fast and then mask it, you get this long tail of errors. And it's natural to say, look, people just didn't see it sometimes. And I think this is interestingly different than the memory situation, because in all the memory tasks I just showed you, working memory, long-term memory, everyone would acknowledge the items are all seen by the participants. Everyone saw them. And so the saying they're all represented with some amount of noise added to their representation is sort of not a huge leap, right? Like, it was processed by your visual system. Everyone acknowledges you saw it. And so I have been asking with Michael Cohen and Jonathan Keefe is, well, what about in these perceptual awareness tasks where people report not seeing some of the items? Are you going to find a different result? And so I'll quickly show you an example of a backward masking task, which seems to me the simplest version of these tasks. I don't know what consciousness people think about this, but effectively I'll show you a task where I'll show you a very low contrast orientation, and then I mask. And in fact, in our real experiment, we use dynamic masks, but I'll just flash up this one mask because in PowerPoint is all I could do. Okay, so what I want you to do is remember the orientation of the grading in these next two trials, and just see if you, and I'll flash it up really fast and mask it. We'll see if PowerPoint keeps up with a quick presentation. Okay, so try to remember the orientation of this grading. I flashed it up and masked it, and then you have to report on a wheel what orientation that was. In this case, it was something like this dimension here. And again, I can give you one more example of this. And something like that, but with a dynamic mask after, it's basically invisible, and with proper timing, it's basically invisible. Okay, so in this situation, what would we expect to happen? Well, what I've just finished explaining to you is that it has to be the case that there are some large errors, that there is some long tail of errors. That is that that all hard tasks are going to have far away errors, and that's just the nature of orientation representation, or any stimulus representation that's high dimensional. And so the TCC model basically says, if there was no guessing going on here, if everybody saw every trial, but just with a different amount of noise, this is what the data should look like. And then perceptual awareness tasks, there's this sense that maybe there's actually going to be added guesses here. There's going to be some trials where they literally don't see it, and those are going to be uniform guesses. And if we try to fit the TCC model to data, where we take the actual model predictions and add extra guesses, it fits very poorly. In particular, it sort of under predicts the tail, right? Because there's just more guesses. There's more out on the tail than the model says is possible. And so what I'm going to show you is basically an informal version. The paper has all sorts of model comparisons and complicated stuff, but effectively just like, hey, when you do these tasks, does it data look like this? like, are there a bunch of added guesses above and beyond what we'd expect from just, hey, there has to be far away responses. There have to be big errors. Are there extra ones in these tasks compared to memory tasks? Does that make sense? Okay, so the first task I'll show you is one we ran ourselves. This is backward masking, exactly like what I showed you. And we sort of presented the target for 17 milliseconds and then had varying amounts of blank afterwards, varying amounts of time to process it before the mask appeared. And what we find looks something like this. So when you show it for 74, when there's 74 millisecond blank, people are very accurate. They can see the target very well, and the TCC model fits very well that data. But even all the way down to 26 milliseconds of presentation where people are very poor, there's only a very small bump here. It doesn't look anything like a bunch of added guesses. It just looks like what you'd expect if the D prime was very low. Just looks like poor, noisy representation. A lot of noise got added to a weak representation. And so we can do model comparison and say, look, it looks just exactly like what the TCC model said it had to look like for orientation. And that is strongly preferred by model comparison. And so we don't see this. We don't see a bunch of extra guesses. In fact, we don't see any evidence for that at all here. Just looks like what happens if you have a weak signal and a lot of noise. We can do the same thing in that attentional blink task I showed you at the beginning, another awareness task here, where people sort of say you don't see the second target sometimes. And what we find is that when there's a long break after the red target before the green one, you get very accurate, very high D primes. When the red item follows when the green item follows the red item quickly, and you tend to get this attentional blink, it just looks like what happens if you make D prime lower. It just looks like lower signal relative to the noise. We can't distinguish signal and noise, right? We're just D prime is just signal to noise. But there's lower signal to noise ratio here, and no extra guesses. Again, it doesn't seem like there's any extra guessing going on here that you'd need to account for with discrete failures to see it. Just looks like noisier. There are other attentional blink tasks we fit. I think in this paper we fit a whole bunch of different tasks. I won't show you all of them. I just grabbed a few. But the original attentional blink task that was used to claim the discrete nature of conscious perception is this paper with color. You might think color ends up a little more discrete than orientation. I kind of thought that. And we don't find any evidence of that. Here you have to just report the colors of the squares among circles. And when they follow each other after a long way, you get a pretty high D prime. And when they follow each other quickly, you get a low D prime. There's no, again, strongly preferred in model comparisons to just say, hey, this is just the boring model result it had to be. And no extra guessing. The last paradigm I'll mention is iconic memory. This sort of Sperling paradigm, you put up a bunch of stuff and then you cue somebody right after it disappears to one of the items. And the claim is often that, some of the items make it into working memory and the other ones die. This paper is titled Iconic Memories Die a Sudden Death. It's very aggressive framing. They die. And so this is, again, a discrete failures idea, right? That some just don't make it into working memory and some do. And that this has to do with, awareness. And we don't see any evidence of that. Here's the fit of the standard TCC model. It just says, well, hey, the longer you give people to process it, the more signal they get out. So D prime goes up with delay, but that's it, or D prime goes down with delay, sorry. And so again, we just see this looks like just the exact regular thing you would expect without any of these extra guessing. We have some attentional cue things and some other model fits in this paper from other data. But broadly speaking, we just don't find any evidence here that anything different is happening here. Just looks like exactly the same it looked like in working memory and long-term memory. Just given the confusability structure of that stimulus space, it kind of has to be that there's going to be some long tail. This one knob, just signal to noise, seems to account perfectly for data from perceptual awareness paradigms, exactly the same way it does for working memory and long-term memory paradigms. So this seems like just continuous changes in signal strength, not like failures of encoding it or failures of losing it. Even though, like, I totally share the intuition with everyone else that when you look at this kind of data, it looks like a peak and then a flat part, right? Like, I see the mixture model in it. I totally understand why that's intuitive. It feeds into our very binary thinking tendencies. It really seems very appealing, but we just don't see any quantitative evidence for that here. Okay. And we could do that same thing, which was maybe too complicated, where we just ask, well, if you fit the mixture model to these data, does it actually look like there's sometimes really high guess rates and good precision and vice versa, like you'd expect if there were two knobs? And like the answer is no. It looks like it falls exactly along one line in all of these perceptual awareness paradigms we fit. So I only showed you like 5 of these conditions, but here's a bunch of conditions that we fit in this paper. And they all look like they just fall on the same line. They're just worse and better is a good description of how people perform in these tasks, not guesses and not guesses and precision and whatever. Okay. So that's like, we proposed this model. It's pretty simple. I mean, it's not that simple, but it's like pretty much just 360-degree force choice signal detection is complicated. And the thing we're adding is not that complicated. And it has this idea of like, far away items are very far away in representational space. So of course you don't confuse them that often. And when you do, you confuse them all equally. There's one more like signal detection-y thing. Oh, I see that my slides are not updated, so let's see what happens. Oh, there we go. I just had an animation error. Okay, so there's two more signal detection-y things that like will be the first questions that everyone asks, so I just thought I would just explain them. I like almost ended the talk there, and then I added 5 more minutes because I was like, I'm just gonna end up saying this in questions. So I'll just say it now, so you can mentally end the talk. Pretend someone asked me a question, but it feels like I'm guessing. Which is always the first question. How do we account for that? Well, like the standard signal detection view is just like, well, like unbeknownst to your conscious self, there is some continuous signal in your brain. And in perception tasks, this is easy to explain. So this is just like, imagine you're asking yourself whether your phone is vibrating in your pocket. When your phone actually is vibrating, there's much more somatosensory neuron firing than when your phone is not vibrating. And so on average, we're pretty good at distinguishing when our phone is vibrating and when it's not vibrating. Sometimes our phone vibrates and it drives all the neurons and we're very, very confident our phone is vibrating and we're almost never wrong. Sometimes we think we feel a vibration, but we're not totally sure. It's sort of above the threshold. And so we're like, hey, I think my phone was vibrating. And then sometimes we're wrong. Sometimes our phone wasn't vibrating and we feel it vibrate anyway. Or in my case, hear my baby cry when she didn't cry, right? Like any continuous signal, which happens to me all the time. Looking at new parents here. I'm like, was that my baby? Any continuous signal strength here. And the like idea of if it was really a continuous signal detection theory, there's two sort of parts of this, right? One is if you have a really weak signal, if these two distributions are pretty much on top of each other, then you're often going to feel really not confident, right? You're going to have to set your threshold really low, and you're going to feel like you have no idea, even though there's just one continuous signal. And the other is that you're going to experience sort of genuine false alarms, right? Like you really do feel your phone vibrate when it does not vibrate sometimes, or you hear your baby when they didn't really scream, right? Like this green part of this distribution, like sometimes you really have genuine false alarms. And so I'll just show you quick evidence in this model that both of these things do happen in these kinds of paradigms. And that therefore this is a pretty simple way to think about it. Okay, this is a really, this slide is visually complex. Okay, here's what I did. I imagined we saw 6 colors and that we encoded them all equally well. And I turned these distributions sideways. This is just the same bumps I showed you before. So when you saw pink got a big boost in familiarity, and then it got corrupted by noise. And when you saw purple, it got a boost in familiarity, and then it got corrupted by noise. And at the end, you have these distributions. Does that make sense? I just turned them sideways to fit 6, but usually this follows a different slide. Okay, and then of course on some of these items, even on the same trial, if I probed pink, you'd be like, hey, it's exactly this red, and I'm very confident because I have a very strong signal. Like my height of the distribution here is very high. So that's just the signal detection strength, right? Axis goes this way. Whereas if I probed you on this one, you'd say, well, I really have no idea. It's like there's a whole bunch of things that are all medium activation. I'm not very sure what the answer is. And so you're going to have, even though you had the same encoding strength, just because you're adding noise, you're going to have some that end up well represented and highly confident and some that don't. Even though the generative process here is they all got encoded the same way and got the same amount of noise added to them, right? So the noise creates differences between the items. But the generative process doesn't have any guessing or anything. There's no objective guessing here. But some of the items are going to feel like you have no idea what the answer is. You're going to feel like you're guessing. You're going to have low confidence in these. And if you just ask in data sampled from our model, if you have a really strong memory signal like D prime 4, then on average, your memory signal that wins is going to be super high. They're all going to look like this. They're all going to have really strong signals when you only have one item and your D prime is really high. And so you're going to have really strong signals. What I'm plotting here is the winning signal's strength. By the time you get to like 6 items and a D prime of 1, the winning signal is going to have way lower strength on average because you're only adding a little bit of signal to the correct answer and then corrupting it by noise. And so you're going to have the winning signal is going to end up not being that strong. You're going to have way more trials like this when your D prime is lower. And what I've done in red here is I've just color coded what signals happen pretty regularly, even when D prime is 0. When you just didn't see anything, you'd expect to sometimes see signal strengths this high. So this is just like this threshold, right? It's just like me putting a threshold on like, what would you expect even if nothing happened? And what you see is that at set size 1, you should basically never feel like you don't know. At set size 3, you should sometimes feel like you don't know, that you have a signal strength consistent with having seen nothing. And at set size 6, this should happen a lot. And we can just figure out mathematically, this is like a 1% feeling of guessing, a 20% feeling of guessing, and a 60% feeling of guessing. And then it turns out that people have collected exactly this data, literally a binary confidence scale. Do you feel like you're guessing or not? In fact, Kirsten Adams' paper with Ed Vogel and Ed O did this. And here's what they found. They found 5% people feeling like they're guessing at set size 1, 23% at set size 3, and 58% at set size 6, right? So keep in mind that our generative process here is just signal detection, which is different strengths, right? But if you just sort of set a threshold on like, I shouldn't listen to things that could be pure noise, those are just guesses, then you end up just with exactly this data, right? So this generative process has just noise added to each item. But if you put a threshold on like, hey, I shouldn't listen to my brain when there's just noise there, then you can easily explain why it feels like you're guessing, right? This is just a low confidence state of feeling like you don't know. And of course, it happens more when signals are weak. Just had to be that way, right? Okay, so that's one half. And then the last half, the last 2 minutes here is the other half, which is that if you think the same thing is happening, that they're sort of with weak signals, you will experience genuine false alarms. Then when there's no signal, you should sometimes be highly confident there was one, right? This is like the basic signal detection. Like sometimes you feel your phone vibrate when it didn't vibrate, right? Or sometimes you detect light in your retina even when there was no light, and classic detection theory stuff, right? Okay, so we've done lots of stuff on this. I'll just show you one experiment that I think is kind of cute, where we presented people 4 colors and then probed them on one. And we have 2 ways we probe them. Sometimes we say, hey, what color was in the top left? That's a standard task. Sometimes we say, hey, you can choose your favorite item and report that one. And so it's a 2-part response. First, you click which one was their strongest memory, and then you click what color it was. This is a choose best paradigm. A bunch of people have used this in the working memory literature. And the trick is that we sometimes show people 4 items and then mask them and then do these 2 tasks. But on a few trials, we actually only show them one thing and then we mask 4 locations. And then we do this, and we sometimes probe locations there were no items at. And we designed this experiment where we present these not all at once to make this basically visually impossible to see that there was not an item there. So people don't really have a meta awareness there was only one item. I'll show you a video. I don't know if it'll come through, but here's what this looks like. It's very fast masking, and the items appear not all at once, because then you get a really good transient if they're all at once. Okay, so here's what this looks like. It's very, very hard to see that on one of those trials, only one item was presented, right? And so people broadly just believe us. They don't think we're tricking them, and so they think there are 4 items presented, and then get probed on this. Okay, how does this answer this question? Well, what we can ask is basically like, if we've tricked people into believing there's 4 items here, they're checking 4 separate locations for signals, then they should sometimes experience really high confidence false alarms, where they falsely have a very strong memory of a location that had nothing in it. And in fact, the very first experiment we did on this, we just asked people their confidence. And we found that if we probed without the choose best thing, and we found that if we probed a location that had no item, people gave us their highest confidence scores like 15% of the time on a location that had no item in it, which is pretty much broadly exactly what you'd expect for the D prime they had. But we thought it would be nice to avoid confidence reports. And so we did this choose best technique, where instead people choose their best item. And here's what happens. First, just to ground us out, if we show one item out of 4, that's the interesting condition. and we force them to report that showed item, so we queue that location, we get a D prime around 1.52. I'm showing this distribution as like a half distribution. It's just the absolute value of their error. I often plot them this way just to fit more things on the slide, but you can project this the other way and make it that symmetric bump if you're used to that. Okay, and so the idea is that there's one item with a real signal with a D prime of 1.5, which we know, because if we queue that item, that's what they have in their mind. But there's also 3 items that actually have D prime 0, because we didn't show anything. But each of those has some noise associated with it. And sometimes D prime 0, like I was trying to show you on that previous slide, sometimes D prime 0 results in a pretty strong signal, right? Like here, the maximum signal at this pink is 2.4, which is pretty high. Here, this maximum signal is 2.9 at this green, which is at this blue, which is almost as high as the actual item. And so from our model, we can just say, hey, if what they have in their mind is a D prime of 1.5 for the real item and D primes of 0 for the other items, but with noise, with genuine noise that they actually are checking, thinking it's an item, how often should they report one of these items that didn't exist as their strongest item? And what should happen to this item in that situation? And so what we predict from this data is that 35% of the time or so, people should choose as their best representation an item that was not there. Because that's how often a D prime of 0 should result. 3 D primes of 0 competing should result in a higher signal than a D prime of 1.5. And what we find is that around 30% of the time, people choose an item that wasn't shown as their strongest item in this scenario. And so naturally, if we look at when they choose their best item to report, they actually have lower performance than when they're forced to report an item that really did exist, because there's no right answer at all for the ones where they're reporting something that they didn't see, right? It's a randomly chosen, unshown item. Okay, so 30% of the time they pick an item that wasn't shown as their strongest. And then the really interesting part here is that what happens when we ask them to choose their favorite item and they actually pick the presented item as their strongest? Well, what we would predict is that this should actually be better than when we force them to report that item. And that's because they're only going to choose it as their best item if it actually was stronger than all these D prime 0 items, right? If these are genuinely competing with it in memory, then when they choose this as their strongest, it should be because it had a good representation, better than these other ones that didn't exist that they were checking. And that is what we find. We find a considerably higher memory performance when they report this as their favorite than when they're forced to report it. So this suggests people really are like actually considering these locations in like the noise in those locations as items. Like they're genuinely sometimes believe these were the strongest items that they're reporting. Okay, so this is like both halves of this, right? Like the more signal detection-y, if it worked like this, you should sometimes feel like you don't know. And that's true, subjective guessing, but not like objective guessing. The generative process is always the same, but you subjectively feel like you're guessing, and you should experience genuine false alarms where you didn't see anything, but you nonetheless feel like you did. Okay, that's it. That last part took a long time, sorry. And so noisy decision-making where items differ only in strength or signal to noise, D prime seems to account for performance across a wide variety of these tasks, these continuous reproduction tasks. With no concept of discrete failures necessary, you just don't have to add that assumption. It just doesn't add you anything to add that assumption, and so it loses in model comparisons. This works really well to account for memory and different stimulus spaces, set sizes, encoding times, delays, blah, blah, blah. I only showed you some of that. And accounts for this degradation of perceptual awareness across a variety of perceptual awareness paradigms. And the broad idea here is just that this long tail of errors, these faraway errors, are just a natural consequence of rich high dimensional representations. That's just how similarity structure works in those spaces, and not evidence of lots of guessing. And that continuous noisy signals like this detection theory version predict high confidence false alarms and the subjective feeling of guessing perfectly naturally, in line with what we do find in the data. Okay, thank you to all of you for listening, and to all of these folks.
Fantastic. Thanks so much, Tim. First, we should unmute and give you a round of applause. Thank you so much. fantastic stuff. And I'm looking forward to the discussion. So please do, if you have a question, please do put your hand up, and then I will be able to see that. So yes, Josh, I think, has already got his hand up. So why don't you go ahead?
You're muted, Josh. You're muted.
You're, yeah.
Good. You didn't hear me saying, oh, fuck. Oh, fuck. It's really elegant that you've got just one parameter to explain all of that stuff. And in the last bit of the talk I found most interesting, the question about why does it feel like I'm guessing.
Yeah, that's why I added it.
and in that, you've got a sort of a criterion for guessing that's static. That's probably an oversimplification, but it's the common oversimplification in signal detection theory that your criteria are static. And I was just wondering if we relaxed that simplification and allowed the criterion to fluctuate a little bit, as there have been evidence from various types tasks that the criteria do fluctuate in certain tasks, maybe not these, maybe not this particular task. That would add like a second parameter to your model, the variance of the criterion. But then it struck me, well, if we're going to allow the criterion to fluctuate a little bit, maybe the reason for that fluctuation is that the noise is actually fluctuating a little bit, and the criterion is just sort of tracking it. So that we're some trials we just feel, oh, I really remember that well, and some trials we didn't. So we're going to have a wider criterion for familiarity or confidence or whatever you want to say. But then, if we're going to allow the variance of the noise to fluctuate on a trial by trial basis, wouldn't that be sufficient in itself to produce the long tails? And you wouldn't need your exponential distribution of discriminability. Sorry for a long question.
So taking the last part first, which is that it depends on the shape of the noise, right? Whether it's gonna produce this. So yeah, so if you just make your noise have the inverse shape of the familiarity function I used, then of course you can. I mean, we're adding them together before we make any decisions, so you can move that shape to the noise if you wanted to, but it wouldn't save you from having to have that shape somewhere, right? You have to have somehow all the far away things compete the same, and the close together things to the target have less noise or more signal or whatever, right? The criterion issue, yeah. So you'll notice I almost only talked about forced choice, this continuous reproduction task, which is where we have one parameter, right? Because there it's trivial to say the decision rule is the max of your choices, of your signals, right? Of course, the second you add confidence reports or even just guessing or not guessing, now you've got a criterion. Every model has to deal with that, right? And you've got all the complications associated with criteria and whether they drift, and whether they drift more when you have more criteria, and whether they drift more in long experiments and recognition memory versus perception and whatever, right? All those things happen. So basically, I don't like that, and John Wixton likes that. So John does all the things about recognition versions of this, and I try to keep myself in forced choice situations where I don't have to think so much about it. Just I don't know. Just depends how much you like modeling decision rules, right? So almost everything I showed you keeps the decision rule as just the max rule, because it's just forced choice. And yeah, all sorts of more complicated things have to happen when you don't do that. If you just do recognition, if you show a color, like I showed at the beginning, like green, and then I showed purple, and then asked you about green and purple. Well, like now, because green and purple are like effectively infinitely far apart. That's just, this model is just signal detection, right? There's not even any generalization. It just is signal detection. So you can have, you can do all the ROCs and all the stuff. And we've done some of that stuff in working memory and found pretty equal variance looking ROCs with pretty stable looking criterion for confidence. It looks more like perception than it looks like recognition memory in our hands, basically. I don't know. I said a lot of things, but you said a lot of things. So I don't know if I answered your question.
Great. No, it was, two sets of interesting things. So it was good to hear that discussion. Trey, you have a question?
Yeah, thanks. Can you hear me?
We can. Yep.
Great. Thanks so much, Tim. I really enjoyed the talk. I was hoping that you could maybe briefly offer some thoughts on the differences between your TCC model and variable precision models. Hopefully, it's not like too terribly technical jargon for me. It would just be helpful in thinking it through. So, like, what's the difference, for instance? And I think there are kind of two parameters in variable precision models, but like both, like with minimal formality, what's the comparison? And then have you run, like, are you seeing similar results in terms of like the TCC model generally outperforms the variable precision model, or yeah, I'll sort of leave my rambling there.
Yeah, so we haven't spent, so I like really don't enjoy fighting a lot about fits to data that are all fit pretty well. Like, I don't think the reason you should believe the mixture model isn't as good a fit to the data as TCC is that it like fits the data better. I think you should believe it because look, we showed those two parameters don't actually vary separately, right? There's only one knob. And like we can make all sorts of, the TCC paper makes all sorts of like novel predictions, like, hey, look, if there's really one knob. And so, for example, in the variable precision model, the same thing is true, right? They don't a priori have a way of saying, like a priori, you can have any amount of variable precision. You can have any distribution mixed together, right? And whereas we're saying, look, it's always exactly the same. So we can do cute things like say, what if I just give people that forced choice task between purple and green? And I just measure D prime. It's just a 2 AFC task. Our model says that is 100% sufficient to measure memory. And I can take that 2 AFC D prime and predict the full distribution of errors they would have if I gave them 360 choices, or if I gave them 8 colors to choose from, because we're just saying, look, once you measure D prime, you figured everything out. Everything else is just about which options you offer people. And so we've done all sorts of things where we ask the model to generalize from, like, if you just measure D prime in one task, can you use it to predict performance in another task? Those are all things that are just broadly just beyond the scope of most of the other models in this world, right? Like the variable precision model, the neural resource model, like they just are only models of continuous reproduction tasks because they're not grounded in the same signal detection theory stuff we're doing here, right? We're just generalizing signal detection theory. So we're comfortable with a 2 AFC task or an 8 AFC task or a continuous report task. And so I'd say, like, largely what we, like, all the models fit the data really well. And what you basically have is just like different emphases. So the variable precision model and the TCC model sort of broadly agree that there's no differential noise between the items. We don't, well, there's just all sorts of complications. It's a really, you asked for a simple answer and I didn't give one. But like broadly, I would say what our like broadest take home point is like, look, if you fix the perceptual structure, there's just one thing, and that therefore you can generalize across tasks and stuff. And none of that falls out of the variable precision model. But like in broad agreement, all of the neural resource stuff with Paul Bayes and the variable precision stuff with Weijima, like we're all saying stuff that's highly related and all doesn't allow for discrete failures and says something about high dimensional representations with tuning functions have to look this way. Like that idea is in all of those models. We just wrote a review paper that we pre-printed with Sebastian Schneegens, Paul Bayes, Weijima, and me about this, that has some attempt to connect them in the beginning paragraphs if you want to check it out. It's up as a preprint.
Fantastic. Claire.
Hi, yes, very interesting, thank you. Can I, your video has gone. I can't see, you're back, right, cool. I wanted to ask you more about the overlap in your claims between the working memory and the perceptual awareness. So as I understand, this is all a very similar type of model. And also, so you were saying with the working memory tasks that perceptual encoding was all fine because these are all super threshold and shown for a while. But of course, working memory tasks are relying on perceptual representations, even at delay. And so like with deep and superficial layers being activated during working memory tasks, is it the case that you think that all of like this confusability curve, is that entirely determined, say, by V1 representation, if this was orientation, or is there something else? I mean, is this all perceptual?
So the first pass, we tend to think that the stimulus confusability function, this slide, right? We tend to think that like this is sort of the nature of like distance in the perceptual structure of V1 or something, right? Like maybe not V1. I don't know exactly how to think about all that, but like I tend to think that this structure is somewhere some combination of regions to the back of the head, because like the same thing for faces, you can measure the same thing, is like broadly a perceptual constraint of like, it just is true that if you try to represent this green, it's going to be most confusable with this green because it overlaps in all sorts of tuning functions. And the noise comes from either throwing a mask up or in a perceptual awareness paradigm, or asking people to hold it over a delay. And so we tend to think that there's like, this is encoding related, like this is like seeing it just has this similarity structure in it. And then this is noise from your task. But like, of course, our measures, I mean, even especially when we're using these criterion-free force choice tasks, we're like really not separating out signal and noise, right? Like we don't have any actual, it's just, to me, an intuitive way to think about it. And we have some data, like if you increase the encoding time, you get higher D primes, and if you increase the delay, you get lower D primes, and those are all like broadly consistent with what you'd expect if you turn up the signal and turn down the noise, and turn up the noise. But yeah, no, we tend to think that way. We have one paper, looking at Josh, that tries to apply this to ensemble perception tasks, where you ask people like, what's the mean color? And if you think of each of these as like, given the memory representation you encoded, what's the likelihood of this color? What's the likelihood of this color? What's the likelihood of this color? Like you've got some complicated memory, and this is like a likelihood function basically, right? Then the ensemble task just reduces to like, well, I should just sum up all of these for all the items, because that's saying what's the likelihood of all 8 colors under this, and that fits the data perfectly. So we can generalize from working memory tasks to ensemble tasks using that idea, for example. But like broadly, the idea that this is like, given the representation you formed in your head during perception, what is the likelihood of each color? Which I don't know how that relates to V1, but like
I don't care about V1 per se. I suppose I was just thinking, front versus back of the head. I mean, like with the higher theories of consciousness, like with perceptual learning, whether you can change the shape of that confusability curve through perceptual learning, but in principle, this could be either a front or back phenomenon, right?
Yeah, that's right. And this is like, I think that's true. And this is like pretty much seems to be a pretty fixed property of the stimulus space, right? Like all the data I showed you uses just the same orientation similarity structure for the attentional blink and for working memory, and for long-term memory, it just uses the same structure. It just says like, what if it was fixed? Like it may not be completely fixed across people or whatever, but like we just start with like, what if it was? And that works pretty well. So we haven't changed. And like conceivably perceptual learning would distort this function, right? Like it would look different if you did a bunch of perceptual learning, because it would change the distance.
Yeah. Great. Thanks very much.
All right. John Simon.
Hi, Tim. Great talk and really compelling data, really interesting. I realized that long-term memory was only about 1% of your talk, but I have a particular interest in long-term memory, so I hope you don't mind if I
was trying to talk about awareness. It's a consciousness group.
So in long-term memory literature, there's a distinction between memory for features that are kind of intrinsic to the item. So, features that might be kind of unitized, is the term that's often used. such as color, such as stimulus orientation, some of the other tasks that you talked about in your presentation today, and the sort of the understanding in the literature is that the memory for those sorts of features can be based primarily on familiarity and can be modeled quite accurately using a single signal detection process. But that memory for features that might be less intrinsic to the item, maybe more contextual features, such as stimulus location is one example, might be based on a more complicated set of parameters, dual process signal detection theory, or perhaps just some sort of mechanism that's more complicated than a single process, such as perhaps success and precision might be one possible conception of that. So I guess the question is, does that same distinction in the literature applied in working memory, my ignorance of working memory, I don't know whether that's true or not, and sort of then would you predict in the long-term memory task, or perhaps in the working memory as well, that if you used a task that was based on something contextual, such as stimulus location, whether you would see the same very close fit by a single process type of model?
Yeah, so that's like a whole different talk, and I have a very different conception of this than the literature does. So I think that's why it's a whole different talk. I will say empirically, we have never found a scenario where it looks like there's like this added recollection failure in any task where we use this continuous reproduction task. So we've done several long-term memory papers. This paper is about long-term memory for color, but in all the refitting other people's data that we've done, which we haven't yet written up for long-term memory in the way we did for the perceptual awareness, we don't see any evidence for any of those distinctions. I broadly think that conceiving of this as like the same way I tried to argue for like orientation with tuning functions, like you store a stimulus, you have some very high dimensional memory trace, and depending on what you ask, you collapse that down to a memory match signal differently, right? If you ask me what color was it, then I end up with one signal detection axis that's like memory match for color features. If you ask me about location features, I'm going to end up with a different axis, right? Because I'm going to collapse the match of this location to this signal is going to be different axis. So it just has a different axis, right? And so signal detection is like this convenient way of saying, well, if I collapse it down to the unidimensional decision I'm asking people to make axis, what does it look like on that axis? And so I tend to think, well, the dual process is sort of a funny way to talk about asking someone a different question gives you different information back out. You ask someone a different question, they collapse it differently. They all look kind of signal detection-y for the most part, and you end up with different memory match signals, and you can model that pretty simply. And if you do these continuous reproduction tasks, we don't ever find any extra failures in any of those features. It just looks kind of like what you'd expect from that. But yeah, I know obviously that's controversial, and there's lots of long-term memory papers doing things like this and arguing they are guesses, including me, right? This paper is like a rebuttal of my own 2013 paper. Like I was wrong for sure. Like it looks like a mixture model. I was all on board with mixture models. I wrote the toolbox many of you probably used to fit mixture models, right? I was all on board until we figured out that it didn't seem to be true. And so yeah, so anyway, at least in our hands, we don't find any features that look more. I mean, you can find features that are very peaky, like if your similarity structure is super peaky, like location, like the noise is very small, like even a tiny change in location is effectively an infinite change. Then you can find data that looks very peaky and very mixture-y, right? But that's also just what you find in the similarity structure of that stimulus space, right? It's like the case that a small change in location is almost the same as a large change in terms of like being infinitely discriminable. So yeah, so I don't know, in our hands, it seems like if you hold stimulus dimension constant, it always looks like this. And there's interesting questions about why some stimulus features give rise to more peaky distributions and look more binary, but not like a really obvious difference. But of course, that's like a really strong null model. Like that's like, well, we haven't found anything that doesn't do that. And that seems kind of useful to think that way for now. But like, yeah, I'm sure there's really complicated edge cases. I mean, like Josh was pointing to criterion noise. Like there's lots of things you can model, and this is a very first pass. Like, hey, we don't find any qualitative failures of this approach.
All right. I was wondering if I could ask a question that follows up to some extent on what Josh was asking before about setting criteria for guessing, because I was very interested in that part of the talk, and it was striking me that, in a sense, from the subject's point of view, there is something discrete there, in the sense you're asking them a discrete question. Do you feel like you're guessing or not? And perhaps that discrete decision then takes on a life of its own, like 300 milliseconds later you're remembering yourself as discretely guessing, and that's maybe what underpins this intuition that we are discretely perceiving. And I'm wondering that here in your model, it seems that essentially you can predict where that criterion lies for generalization to this other paper based on the D prime alone. And so that would imply perhaps something quite deep about how people set that criterion. That it's nothing to do with the stimulus or the task. There's some maybe modality specific, maybe even very domain general, just way of knowing what your noise is. So I'm just wondering whether you've thought about like how that gets set.
Yeah, so the line I'm drawing there in red that matches things is basically just the optimal decision boundary. Like we know D prime and we know what 0 looks like. So I'm just drawing the max likelihood decision boundary, right? So that's just, there is something special about that, right? As you know, there's something special about that boundary. It is like a very reasonable boundary to set if you didn't have any reason to have any different criterion. If you're waiting for an important phone call, maybe you shift your criterion down and have more false alarms and detect every phone ring. But yeah, so what I'm doing here is I'm just saying I should have plotted the D prime 0 distribution, but I'm just plotting just the decision boundary. That's just the optimal boundary given 0. But note that here there is no 0. Like there is, like, on a given trial, all colors feel familiar. So yeah, so insofar as this does match the decision boundary, it would suggest what people are doing is saying, like, my criterion for guessing should be what would happen if I didn't see anything. And we don't ever have trials where they don't see anything. So it's like kind of weird, right? So it's like mathematically convenient to just assume that line. But yeah, there might be something deep about saying subjects really do assume that line. With when you don't give them any hints. So obviously, like Kirsten, Adam, Vogel, and O in this paper, they're like trying to argue that these are just genuine objective guesses. And so they just had a criteria. They just asked people, are you guessing or not? For a different reason, right? They wanted to say it's uniform when people are say they're guessing. And they have a whole complicated story built up about this. So if you're a thresholdy person like these folks that think some items are represented and some are not, then you have to say metacognition is really noisy, because it turns out when people say they're guessing, sometimes they know the answer. And when they say they know the answer, sometimes it looks like they make a far error. Obviously, signal detection is perfectly fine with that. Couldn't be any other way. But they have to have multiple levels of noise and complicated stories, right? So they have like a whole series of papers with relatively complicated stories about metacognition that in our hands just look like what happens if you set a criterion in signal detection. So yeah, so I don't know if it's really deep that I colored these red based like here. We haven't published anything on this. This is just like an informal way to think about it. We have done a bunch of data on confidence, like where we ask people 1 to 6 confidence in continuous reproduction tasks. And you don't find like a perfect, like you do find people tend to be a little bit stronger, and like they tend to have more representation in their strongest and weakest confidence bins than you'd most naturally predict from this kind of model. Like you do want to add a little bit of variation in D prime between items probably. And like, how could it be any other way, right? Again, this is like kind of a null model. But like, if I present 8 items, you're probably not encoding them exactly equally with only the noise, independent noise accumulation. I mean, maybe, but if I showed you 100, that couldn't be true. Like some are gonna be in your periphery, right? So like, there must be variation between items, but just like assuming none at all gets you pretty far is what we're saying. Not like I would bet my life there's 0 variation in D prime between items. Just like, certainly you don't need to say half the items are gone. But yeah, I don't know. The criterion issues get interesting. The only thing we've done on that is to simplify to just change detection, just like, was it green or red? And then we have a couple papers doing, and then of course this model just reduces to equal variance signal detection. And then that looks pretty good, actually. We have a bunch of papers doing that, basically, showing that seems to account for a bunch of data people had previously claimed looked more thresholdy. Yeah, thinking about the 360 choice version with criterion gets very complicated very quickly. Yeah.
All right. Are there any other final questions? Okay, well, I think in that case, we will leave it there and we'll wrap up and thank Tim again for a lovely talk. Thank you so much, Tim. Fantastic.
Thanks for having me. It's nice to be able to visit London from my office.
And thanks also to your family. I know it's not easy giving a talk over breakfast when kids need to be got ready.
The sun is up now, though.
Okay. Yeah, exactly. Yeah, well, thanks so much for doing that early doors, your side. That was great.
Cool. Bye, everyone.
All right, take care, everyone.